Good afternoon, everyone. Thank you all for showing up today. And it's my great pleasure today to introduce Katrin, coming straight from Vancouver to talk about carbon sequestration. Just a few words before starting the seminar. Katrin is currently a geologist at CarbFix, and she is also a PhD candidate on carbon mineralization at UBC, University of British Columbia. And before that, Katrin acquired her master at UBC on serpentinization and implications for carbon mineralization and nickel mining. Before moving to Canada, Katrin completed her bachelor from the University of Iceland and working on volcano monitoring in Mexico. And today she's gonna speak about how we can store sparkling water, I guess, with mafic rocks. So it's all yours. Thanks for coming.
Great. Just testing. Is the sound okay? All right. So hi. Thank you. Thanks for being here. I'm really happy to be here. My name is Katrin. I'm going to tell you a little bit about CarbFix. So CarbFix is a technology that stores CO2 in less than 2 years, permanently and safely in rock. And as we all know, the climate emergency is upon us, and we need to all act fast and act together, and that will need innovative solutions, and we'll need to work on all fronts in parallel. So I just want to start with, this direction, sorry. So I just want to start with some numbers. The new report by the IPCC has lined out different scenarios, how we're going to reach the target of 1.5 degree global warming. And there are many different things that we need to focus on, including switching to renewables. We need to be more efficient with the energy we have, and more things such as carbon capture and storage. In this graph, sorry about that. In this graph, you can see different scenarios that they've lined up for the next 40 years and how we're going to reach this target. And all of them include carbon dioxide removal to some extent. So we will need to do many things, and that includes removing CO2 from the atmosphere. So before we go any further, I just want to ask one question. If you could raise your hands, who has heard of the abbreviation CCS and CDR before? All right, a few of you, great. And who knows the difference of them? Okay, let's go over that. So when we talk about CCS, or carbon capture and storage, we are talking about capturing CO2 from point sources. So we have power production, we have some industry or a factory that's emitting CO2, and we capture that before it goes into the atmosphere, and then we store it. When we're talking about CDR, or carbon dioxide removal, we're talking about historical emissions. So we catch CO2 directly from the atmosphere, and then we store it. But both of these things have to include the storage side of things. So we need to capture in some form from some source, and then put it in the ground or put it somewhere safely. I like these schematics on the right-hand side here, because they just show very simply all the different ways that we can do this. There's a lot of innovation going on in this space. If we start at the top, we have the different CO2 sources, or different CO2 capture. We can do it from direct air capture. We can use some technology like magnesium looping or point sources. And then we can store it either via exit two ways, so on the surface, atmospheric pressure and temperature. And that's either through enhanced weathering, for example in farmland, where we distribute crushed material, or through mine tailings, which is there's a lot of research that goes on that. So it's just waste from the mine, and that waste can react with the CO2, both capturing it and storing it in one process. And then we have the in situ ways. We have the conventional CCS that uses sedimentary rocks, or we have basaltic or serpentinite rocks, and we can inject CO2 into them where mineralization happens and the minerals are stable over geological timescales. So the bottom line, before I go any further, is that we will need carbon capture and storage or carbon dioxide removal to some point to reach the global climate goals. In the next 40 years, we need between 100 to 200 billion tons of CO2 to be captured and stored. So it's quite a big problem, but we will need to try. And that brings us to CarbFix. So what CarbFix is, it's a technology that stores CO2 in less than 2 years through our technology that imitates natural processes and accelerates the speed of them. You can see here an image of a core from one of our sites. So it's a basaltic drill core, and you can see the white specks all over. These are the carbonate minerals, the calcite, and this is what the CO2 looks like after it gets solidified. Just a little bit about our history. We started back in 2007. It was an idea on paper between the Reykjavik Energy, which is a geothermal energy in Iceland, and 3 universities, University of Iceland, CNRS in France, and Columbia University in New York. So it was collaboration from the start. And in 2012, so in just 5 years, we started injecting with a pilot injection in one of the sites. And then in 2014, we started industrial scaled up again in 2016. And in 2017, we've been working with direct air capture as well. Our plans for the future and from now on are to scale up even more and to go commercial. So here's just a small schematic of what the geochemical framework for this process is. So first we have some rocks. We have basaltic or other reactive rocks, and these are rocks that contain high amount of divalent cations. So we have a lot of calcium, magnesium, and iron. And these rocks, when they interact CO2 that's been dissolved in water or sparkling water, they react with the CO2 and they form carbonate minerals. In the case of basalt, we have the calcium end member most likely happening, so calcite forms. And you can see again the little white specks that precipitate in these porous spaces. And this is all based on the natural analog that we understand quite well from basaltic rocks all over the world. So the first image are just some pretty images from drill core where you can see the basalt, you can see the vesicles, so the porous spaces where the calcite has formed. Here as well, a little bit smaller and in fractures as well. So we know this is happening. The CO2 that formed these calcite minerals is just natural magmatic degassing in volcanic regions. On the right-hand side, we have these 3 different graphs from 3 different geothermal fields in Iceland, varying in age. So we have the youngest field, older and older, and in the oldest, you can see that there's most amount of CO2 that's already naturally been sequestered in it. I think it's more than 100 kilograms per cubic meter squared. So the potential is huge. When we go to areas that are relatively young and CO2 has not already mineralized in it, we could theoretically store a lot of CO2 in them. So we have 3 different pathways that we're working on how we can do this and how we can scale up. The first is the cheapest way. We have, at the same location, capturing of CO2 from a point source emitter, transported a short distance or no distance at all to a favorable rock formation where we do the injection. Then we have other locations where maybe we don't have the favorable rocks at the same site as the CO2 capture, and we can transport them to these hubs. And lastly, we can do direct air capture or CDR, so we can capture CO2 from the atmosphere. We have nearly a pure stream of CO2, and we can inject that into the ground. A little bit better schematic can be shown here. So we have something in the beginning, for example, a power plant or a factory that's emitting a lot of gases. And these gases can be variable in composition. We can have CO2, we can have sulfur, nitrogen, water vapor, etc. So we grab all of them, we just capture it, and we pipe it into what we call the scrubbing tower, or the shower, as I like to call it. Because what happens is we also put water into this tower, we increase the pressure a little bit, and as the water drips down and the gases go up, the gases get dissolved into the water, the gases that we want depending on the pressure. So we want the harmful gases like CO2 and the sulfur, and the rest of the non-harmful gases are just released back into the atmosphere. And then we make sparkling water. And this step is really important because we are forming a solubility trapping. The CO2 is now in the water, in the sparkling water, and we can transport it very easily, non-corrosive way. And we transport that at our site. Currently, it's roughly 1 kilometer distance to an injection well, and we inject it to a depth between 500 to 2,000 meters into the basaltic rocks, or the mafic rocks. And there, the CO2 sparkling water starts interacting with the rocks and forms, via geochemical processes, the carbonate minerals. And once that happens, we have the mineral storage trapping. So at first we have solubility, and then we have mineral trapping. And that, once you form minerals, they're stable over geological timescales, and then it's safe and stable. So a little bit about where we've come from and where we're going. So we started in 2012 with just a small pilot, 240 tons of CO2 dissolved in water, injected underground, relatively shallow, 500-meter depth, and then it is also in low temperature regime. The map here shows where we are at. Here's a little picture of Iceland, and we are located in the Hengill or Hellisheiði geothermal site, which is just 40-minute drive from the city center. And this, as you can see on this map, there's a lot of fracturing. It's actually a triple point between plates, so we have a lot of permeability in this area. And what they found via geochemical monitoring is that in less than 2 years, all the CO2 that got injected had stabilized and formed minerals. And we found that out in the monitoring well, we did geochemical fluid sampling. Then we started, more pictures. This is how it looked like. It's a bit chilly out there, and actually there was a lot of problem in the beginning just because the pipes would freeze. So there's a lot of extra things that you need to deal with when you're starting a project like this, but they figured it out. And then in 2014, we partnered up with the power plant, the geothermal power plant, captured their CO2. You can see the scrubbing tower here, which was the schematic before. So here the different pipes bring in the gases and the water, and then there's another pipe that transports the sparkling water to the injection site. And we doubled the amount in 2016, and we're doing at this site both CO2 and H2S. The CO2, once it's underground, forms calcite, and the H2S actually forms pyrite, which is quite fun. This was at a lot warmer temperatures, deeper levels, and we've been going since 2014 in the same few wells. And again, they found the same result, that over 95% of the CO2 got mineralized in less than 2 years. But we did further work, and we found out that actually most of the CO2 got mineralized in the first 4 months. And this was really a breakthrough because it showed how fast these reactions are happening. And it was a lot faster than was previously believed. And then I just want to mention one more thing here, is that a lot of people always ask what's the cost of all of these things, because if we're going to scale it up, we need it to be relatively cheap. And we found out the whole process of this in the industrial case, including capture, transport, storage, and monitoring, was less than $25 per ton of CO2. And here's just a snapshot of what's happening within the geothermal field in Iceland. So we are working at this site here. This is our flagship pilot site and where we've been working, the Hellisheiði power plant. We just got a grant from the EU now that will let us go to 95% efficiency of all the CO2. And just as a side note, because I know some people ask, aren't geothermal power plants already carbon neutral? Why are you doing all of this? But geothermal, we are actually tapping off volcanic regions, so we have like natural CO2 from the ground, and we are releasing them to the atmosphere. So they're still important, and we still need to take that into account when we're doing carbon accounting. So it's not fossil fuel CO2, but it's still CO2. And then we started now, or we are about to start. We've been setting it up. It's about to go. pilot scale in another geothermal field close to this one. And lastly, we're going to be working or starting this year on another geothermal site in the north of Iceland. So exciting times for the geothermal industry, but there are also other industries that we need to work with and have CO2 sources. So you can see this little diagram over here showing very rough the concentration of the CO2 in gases from different sources, and that's really the important thing, because as you have higher CO2 concentrations, it's usually cheaper to capture it. So we can store it, inject it, dissolve it in water, and then store it. If the concentration of CO2 is too low, we might be able to do an extra step. So you have a low concentration of CO2, you can do an extra step to concentrate that CO2, and then you just couple it in the same way as with the geothermal. And we started collaborating with heavy industries in Iceland. We have a few aluminum smelters in Iceland that we're going to be working with to try to test these things. Additionally, we've been working with the waste management facilities. They have CO2 emissions when they burn the waste or the garbage. And we're working at the site. Here's a map of Reykjavik, the main city in Iceland. The site we were before was somewhere over here, and now we're going to be working in this site because it's the place of the landfill. And this is really exciting, this project, because it's the first time we're going to be injecting into older, less permeable rocks, and they're slightly different in chemical composition. So we'll see how that will go. Just for fun, I put up here a table if anyone's interested in the gas composition, because there's a big variety if you have a geothermal source of CO2 or if you have a landfill source. And for example, as expected, we have more methane when we burn waste. And that brings us to pathway number 2, when we're using mineral storage hubs. So the overall idea is that we have CO2 capture in Northern Europe. We have power plants, factories, etc. We can capture the CO2 there and transport it via ships to Iceland, to a harbor. This is actually Straumsvík, which is one of the Rio Tinto aluminum smelters that we're going to be working for this first project. And right behind, so the ships will come here. There'll be a storage on site to keep the CO2 until we're ready to inject. And the wells will just be behind these buildings here. And this first one is called the Coda Terminal. We've already started drilling, and the pilot will take place this year. And the idea is that by 2031, at full capacity, we'll be at 3 megatons of CO2 per year. And then if this works out, and we've shown that it works at this scale, we can start replicating these mineral storage hubs, both around Iceland and elsewhere in the world. And for the last pathway, direct air capture and storage, this is a really exciting field, and there's a lot of innovation going on right now with different types of direct air capture, because there's a lot of potential and there are a lot of benefits. For example, you can have these DAC technologies located theoretically everywhere around the world, because once the CO2 is emitted to the atmosphere, it homogenizes really quickly, and you can have a capture site somewhere else where you are maybe nearby to favorable rocks. So you can couple these things together. You can also sell carbon credits because you're removing historical emissions and storing it permanently. This accounting and industry has started where you can then sell carbon credits for offsetting other things. One big limitation that's often talked about is that it's usually quite energy expensive, but it does vary on the type of direct air capture. They all have different ways of doing it, but usually they need some energy, and they're hoping that it will be similar to the solar panel industry. At the beginning, it's maybe a bit expensive or quite expensive, and then as we understand it and start doing it more and more, the prices will go down. But of course, it would be great if we can couple these at sites like with geothermal, where we can just use the green energy. We work with our partners at Climeworks, which is a Swiss-based company that are the leading direct air capture company in the world. And we have set up this ORCA project. It started in September 2021. And they capture the CO2, and they give us nearly a pure stream of CO2, and we inject it and store it. This project is running at 4,000 tons of CO2 per year, which maybe doesn't sound like a lot, but it has come a long way. In 2017, we started our pilot, so the first one, which was 50 tons of CO2 per year. And you can already see a big difference. Here's basically the prototype, and it's evolving and becoming more efficient. And now the plan is to do the Mammoth project that will open next year. They've already started building it, and that will be 36,000 tons of CO2 per year. So we are scaling up on many different fronts. And related to that, we are building the Stack Innovation Park. The idea is that we want to help different types of direct air capture companies try in the pilot, going from the lab to the field and trying it in the weather and with everything that has the outside temperature and stuff. So the idea is that we'll have renewable energy inside, we'll have permitting, and once they've captured the CO2, they can give it to us and we can store it for them. We just won last year the Elon Musk X Prize for carbon removal with 2 of our new collaborators at Heirloom and at Verdox. These are different carbon capture technologies. Heirloom uses magnesium looping, a California-based company, and Verdox uses zeolites. So many different ways, and it's very exciting what's happening in this space. And then the big question on how can we scale up, and is this really feasible to making a dent in climate change? And we believe so. In the next 12 years, we're aiming to reach the gigaton scale. It starts with doing the demonstration of the Coda terminal, or the mineral storage hub, and then starting to replicate, expand it, make it bigger. We can even hopefully go offshore, so we can use the seawater and go to more locations. And then we can start replicating in Iceland and elsewhere. And the potential is huge, to say the least. The most conservative estimates of the storage potential in the world, if we're only talking about volcanic rocks that are on land, it's roughly 7 times more than if we burn all the fossil fuels. So there's a lot of rock out there, and then if we even think about the offshore, there's even more. So we have rocks, there is potential, and we need to just get going. And if we just zoom in to where we are today, the US has a lot of potential as well for this technology. And in Arizona, there's some volcanic rocks that theoretically maybe could be used. And then, of course, there's the Columbia River basalt and the Snake River basalts in Washington, Oregon area. But there are lots of places around the world where we can think about trying these things and do more and more. So when we think about feasibility in different places, which is the aim, we want to scale up and go to new locations, there are a couple of things we need to think about, which can be summarized over here. We need a CO2 source, and we want it to be at relatively high concentration. We want water, because we need to dissolve the CO2 in the water, and it helps with promoting the reactions underground. We need some electricity, not a whole lot for our technology, but often it is involved in the direct air capture, and a little bit for the injection. And of course the rocks. And these rocks, we want them to be reactive, so to have a lot of divalent cations, and we want them to be voluminous in both spatial and at depth, so we can keep injecting at the same place for a while. And then of course there are other things such as accessibility. We need injection wells and monitoring wells. We maybe want to choose our locations by not being in the highest natural hazard risk areas, and other things that we need to think about. If we talk about these things in a little bit more detail, the water is one of the big things that we need. So we need a lot of water, and this is for dissolving the CO2 to keep the pressure and energy and the cost low. So you can only have one, and we want the cost to be low. You can see the graphs that show this. And the water can be sourced from the same reservoir, from a well, or from another reservoir, either a shallower one or nearby. But just a side note, because we're here in Arizona, the water doesn't need to be a drinking water quality water. It can be water that we wouldn't use anyway. And yeah, because the water and the CO2 is injected back into the same reservoir, it actually keeps the pressures relatively similar, and it just gets cycled through. Related to this, we are trying now to check if seawater can be used, because of course there are many places around the world where we don't have abundant water, and then we can use the oceans. There's been some modeling done, so the amount of fresh water versus seawater in this first graph, that shows the dissolution rates. They are relatively similar between freshwater and seawater. And modeling also shown that the carbonate mineral formation seems to work. Calcite does form in the modeling. And in the experiments on the far right, at the same pressures that we expect, with a little bit of changes, the temperatures, the basalt, carbonate minerals form. Depends on the pressure which type of carbonate mineral forms. Seems to work, and that is why we're now going to the field and testing this. So we teamed up with some Swiss universities who are capturing CO2 in different ways in Switzerland. They're going to try the whole value chain, capture, transport, and then we'll store it for them. And it's actually, they started in Switzerland, so they took a train to, I think, Rotterdam, Netherlands, and then it was shipped, and then the last part from the harbor here, it was moved in truck, just for the first test. So it has come a long way. You can see the CO2 over here for the pilot, and we are going to try this with seawater, and we're also drilling that well right now, and it will be, in the next few months, tested. And then we need to wait, and then we need to monitor it, and then hopefully we can see and say that it works. And this just has amazing potential, because then we can go to places where we don't have fresh water, all the volcanic islands and elsewhere. Another question I get often is, what about the temperature? People say, oh, in Iceland you have such high geothermal gradients. Of course, the reactions would probably happen faster where it is so warm. And we've already demonstrated that this technology works both in 50 degrees and roughly 260 degrees, so that's already a whole range. Both of those tests, it took less than 2 years for all of the CO2 to mineralize. And modeling and experiments have been done from 20 degrees up to 350 degrees. Different ways of testing it, but it all seems to work, at least in the lab. And there's actually, we want it to be warmer because the reactions will happen faster, the dissolution and the carbonation. However, when we have areas that are hotter, we usually have more alteration, and then we maybe have less porosity. So maybe it's okay to be a little bit colder and more in the middle range. Additionally, with seawater, if we're above 150 degrees, anhydrite starts stabilizing, and anhydrite is a mineral that is really good at clogging up spaces. So we actually maybe want to be less than 150 degrees Celsius. So maybe counter to popular belief, colder places might be actually better, relatively colder. Okay, and then my favorite topic, the rocks. Oops. Oh, no. Sorry about that, getting very excited. So we've shown this method in basaltic rocks. We know they work, we've tested it in many different ways, and the question is, can other volcanic rocks also work? So we've done a lot of work on dacite and rhyolite, and it's very great that around the world where we have geothermal operations, which is kind of like the low-hanging fruit to start all these things, there is also dacite, rhyolite, and basalt. So we can maybe go to these locations first, and we don't have any problems with that. So that's pretty great. Then there's also some research into other types of rocks, other types of mafic with different mineralogy, intermediate rocks. Are they plutonic? Are they volcanic? We need to work on that. We need to do more research. There's been some research already that shows that they will work, but we need to do even more. We also have ultramafic and serpentinite rocks. There's been a lot of research on that, and we just need to go to the pilot and test them. And here's two pictures. The first one is drill core images from ultramafic rocks from the project we're working on with the Direct Department of Energy and Rio Tinto in Minnesota. They have an ultramafic intrusion next to their deposit that they're going to be mining for nickel and cobalt or something like that. And the plan is that we can inject into this porous ultramafic intrusion. And then here are some nice rocks of serpentinites in BC that show potential. The GACO project, which is an EU-funded project, is trying to answer some of these questions. We've been working with lots of collaborators and partners, mostly around Europe, on a few different things. We have 2 sites that are in Iceland, basaltic, high temperature, and we're trying to answer questions not just on the rock type, but also can we make the CO2 capture more efficient? Can the monitoring be done in different ways? And can we just make everything simpler and more efficient? And then we have a site in Turkey. Those rocks are actually really exciting because they are metamorphosed volcanoclastic rocks, so it'll be totally different geochemical framework. And then in Germany we have some sedimentary rocks we're trying, but there we're looking more at the monitoring and the injection site. And then the serpentinites, or the ultramafic rocks that show such high potential, is actually what I'm studying. So they're really exciting because these rocks have really reactive minerals, such as serpentine and brucite, that contain high amounts of magnesium. And when we add the CO2 to these magnesium rocks, we can then form magnesium carbonates. Here's a schematic of the idea. If we would do a pilot, we can have a CO2 source, some infrastructure. We can inject the CO2 sparkling water into the rocks, and it will start reacting. And I'm trying to answer questions like, where in BC would it be best to try a project like this? And are these rocks reactive enough? Will the CO2 actually react with them, as we believe from experiments and modeling? And is the permeability enough that we can inject high amounts of fluid for relatively long periods of time? And I've mentioned permeability and porosity quite a few times, and that's because it's quite important. We need relatively enough permeability if we're going to inject fluids into these rocks. We want the fluids to be able to flow through the rocks, as you can see in these modeling images here. We have an injection well, and then the CO2 dissolved water starts flowing through the rocks, reacting with them. And we also need some space, because once the carbonate minerals are formed, they will fill up the vesicles or go into the vesicles. Filling them up will take quite a long time. Actually, this paper here showed that in 10 years, we filled up 3% of the porosity at the first site we've been working in Untitled. So even if we keep injecting, we only fill up a small percentage. So we can be injecting at the same site for quite a while. And there's always some risks and challenges with a big project like this. They're listed up here. Whenever we're working with gas, of course, there can be some problems with that, but we try to eliminate it by dissolving it in water. For the groundwater, will it get contaminated? By dissolving the CO2 first in water, it eliminates or decreases the risks of that. And because the CO2 plume is denser and colder than the groundwater, it usually starts sinking rather than the opposite. So it just goes down and then flows with the groundwater flow. Another question is, will this injection actually mobilize any of the metals? Some of these rocks maybe contain harmful metals. However, all the research to date, at least, has shown that carbonate minerals are very good at being garbage bins, and they just scavenge up these metals and they will get mineralized. But definitely some work can be done more to understand this further. And here you can, on this image, you can just see how the temperature difference and the concentrations move through the rocks. So they start going down, and then they start reacting and interacting. Another figure here is on the seismic risk. Of course, we're injecting fluids into these rocks, and theoretically you could have some movements. But we are building on work that's been done by the geothermal industry. It's basically the same idea. The geothermal industry has been re-injecting brine for a long time. We're just adding CO2 into that water underground. And just for fun, here's a graph that shows all the seismic events that happened at Untitled, where we are monitoring. We have seismic monitors. Before we started the industrial scale operations in 2014, and it's just the amount of seismic events from the geothermal operations. When we started adding CO2, it maybe has less. Of course, this is not conclusive, and we'll need to do more studies, but it seems like at least that the addition of CO2 is not increasing the seismic activity. And of course, we have a traffic light system. We're monitoring it, and if anything would start forming or happening, we can just decrease the rate that we're injecting at. And I've talked a little bit about monitoring. We've tried different ways in the past 10 years. So most of them is, we're talking about geochemical fluids. We have some injection site, and then we have another monitoring well where we analyze. We've done tracers, different types of tracers, calcium isotopes, carbon isotopes, so we can understand what's happening in the underground. We also have at the top, at the surface, we have the CO2 soil flux measurements before any injection took place and meanwhile, and there's nothing that is happening, so none of the CO2 is coming up to the surface, at least that we can tell. And we also have reservoir modeling, so we put all the parameters in, and we can see what we expect from the plume, or how it will react with the rocks. And then we have verification, which is really important when we're working with the direct air capture technology, so we can sell carbon credits. You need to verify them. And we just gave out this last autumn this full-scale methodology. It's publicly available on our website, so you can check it out if you want. It includes the methodology of how we do both the capturing and the storage, and how we are sure that it is safe and stable and permanent over geological timescales. And this is really important both for the carbon credits, but also for being transparent, increasing public acceptance, and just showing what the science is all about. And talking about the public acceptance, there's also, of course, a financial incentive that is needed. So here's a map from the World Bank, where current plans for either carbon tax or emission trading systems, either planned or actually happening, is shown. It varies between nations, it varies between states and provinces. But I can tell you, I've been looking at this World Bank report for the last 3 years, and it is optimistic, because the world is lighting up every year, and it really is changing. And we know that we need the financial incentives, especially the carbon tax really makes things happen. So very exciting times. And I also just put up a few news articles, snapshots I stole from the internet. For example, in the US, there's exciting times right now. Just in December, the administration announced they're going to help kickstart the carbon dioxide removal industry. So in the next, or before 2025, they're going to help scale up 1,000 tons per year carbon dioxide removal project. So there's a lot going to be happening. And I just really like this article because it says leaked, and it was January, just a few weeks ago, and the EU is going to be countering. So there's some competition happening, and it's all for fighting these things. So that's really great. And just to conclude, a few of the pointers and why carbon mineralization works. So it's safe. The CO2, once it is in minerals, cannot leak. So it is permanent over geological timescales. And once that happens, we don't need to have long-term monitoring. We know it's safe down there. The cost and the risk is relatively low, and we can always start by drilling one well, injecting into it, and then we can add more and more wells by scaling up. It also opens up new areas from where we haven't thought of carbon capture and storage. So like the conventional CCS, where we have sedimentary basins, we can go to more locations around the world where we have basaltic or other rock types. And it's based on science, and it has a high public acceptance. And here's another concluding slide on just all the projects that we're working on. We are working with the direct air capture companies. We're going to be scaling that up. We're going to be working in different geothermal areas in Iceland and hopefully elsewhere as well soon. We're going to be working with different industries like the steel and cement. And we're testing the seawater so we can go offshore and different rock types. And then our big project, the Mineral Storage Hub, is opening soon, and then we can start scaling up for real. And to conclude, there are some cute pictures of us in the field, from different locations. The first one is Helliseiði, where we've been injecting for the longest time. Second one is the one we're about to open in Nesjavellir, this second geothermal field. Then some fluid sampling, monitoring, drilling. Here you can see the sparkling water. This is actually a peephole at the injection site, just about before it gets injected. You can look in and see the sparkling water. And it's good if you don't see anything, because that means it's fully dissolved. Yeah, and that's it. Thank you so much. And if you have any questions, I'd love that. And you can also, if you want to have any other questions, you can also look at some documentaries, our website, or send me an email. Thank you so much. Yeah, question?
Oh, wait a second.
Oh, sorry.
Can you use the microphone? That's for the recording. Thank you.
Thanks. Okay, so I think I remember you saying that injecting the CO2 forms minerals, including carbonates and pyrite. Was that correct?
When we include H2S, yes.
With the H2S. So is there any concern with what happens when that pyrite breaks down, or is that all going to be neutral, like the acid that's produced, will that be neutralized by the carbonates, do you think?
The pyrites form around the same zone as the carbonates, so always near the injection well. We are injecting the low pH, so we have the dissolution of the basalt or the rocks, and then farther away we go, because we're dissolving the basalt, the pH increases, we neutralize, and then the pyrites and the carbonates. But like the H2S thing is pretty cool because we can include it, but it's not really our priority because we're prioritizing the CO2. There's another related to that is, what if we go to other industries that have SO2 and not H2S, then maybe different types of sulfide minerals will form. But at the end of the day, we're talking like very small ppms, trace. But yeah, unless we would start injecting like where they were formed and then decreasing the pH again, I think they would it's just neutral, normal stability. It wouldn't start changing, so they wouldn't destabilize again, unless something happens geologically. No. I mean, who knows, but no. Yeah.
Any other
Great,
question?
thank you.
Thanks, that was very interesting. This is probably a complicated question, or it has a complicated answer, but there are likely many different kinds of reactions that result in the precipitation of the carbonate, including ones where it just precipitates into vesicles and others where it's actually dissolving the basalt and a variety of different minerals forming. But, and so the answer to this question probably depends on the type of rock to a large degree, but I'm looking for something that gives me an idea of approximately how much CO2 can be stored per cubic meter of rock as a concentration or amount or whatever. And you showed some pictures that suggested something like a ton of CO2 per cubic meter. Are you approaching some sort of saturation in that case, or do you know how much you can stuff in before it no longer will take anymore?
it's a fun discussion. I've actually spent a lot of time on this because that's usually the first question that anyone asks is like, how much in this area can we store? And it's so variable. I've done very many. I have a whole Excel sheet of different calculations because it depends on, are you using experiments and what type of experiment are you using? Are you using modeling? Are you using the real example that we have from the first 2 days, or like how it worked? And we have min and max and conservative and the crazy ideas. And it's because we're never trying to saturate it. We could theoretically do that, but if you would fully saturate, you dissolve all of the basalt, the number would be very high. But we don't want that because that would just be too much of a change and it takes too long and then you start clogging the rock. So rather we want to just do the few percentages, do less than 10% of the basalt would dissolve and react and form carbonate minerals. And what we're working with now is like less than 3%. But because the area is so large, it goes like 3% here, 3% here, and we can continue for a long time. So the answer is we have a lot of numbers, and I can tell you very, very variable numbers, but because they're not reliable and I wouldn't trust them, I've done the exercise just as an exercise. But it depends. So some of the calculations are theoretical, and then we use porosity. We're like, okay, let's say these basaltic rocks have an average of 10% porosity. What if we fully fill? So volume, fully fill, 10% of the rock will be calcite. We use the molecular calculation. Or you could say, what if it's 10% porosity, but we only fill up 3%? That will be a totally different number. Or it's 20% porosity. And it's a game that we can play endlessly, and it's like it looks cool to be able to say it, but it doesn't actually. But with the serpentinites, for example, so what I'm working on is, it's a bit different because we don't have that much porosity, but we have the natural analog very well described. We know the natural analog very well. It can get fully carbonated, but what we are trying to achieve is just to form it's like when there's less than, it's between 1 and 10% carbonate minerals. So we don't get into the stage of forming talc. We don't get into the soapstones and the listronites. We're just like slightly carbonating the rocks. And then we continue slightly carbonating the rocks because, Does that answer the question? Okay.
Any other question? Okay.
Is there something proprietary about the what CarbFix has discovered, or will it be able to be replicated by other companies, other industries?
So we have a few IPs already, and that's in different parts of the injections, the capturing and the injection system. So no, but we want to work and collaborate with as many people as possible, with different industries and different projects, so we can just be one part of the puzzle, and then we can. And we like working with different capturing, different direct air capture, so we can always accommodate and be one puzzle. But we have these IPs, yes.
Thank you for the talk. At the start of the presentation, you were talking about how much CO2 you can capture in the span of 6 months or 2 years. In those tests, were they continuous flow tests, or are those batches with a fixed amount of total CO2 that you were attempting to capture?
That was from the 2014 onwards, where we're still injecting, so it's continuous.
So how do you measure then how much CO2 has been captured over a fixed amount of time during a continuous operation?
So we did that with the tracers and the isotopes, but it was from the start of the 2014 test. So it was like in the first 6 months, 40% of the CO2 had mineralized. And we could just, because we have these different monitoring wells at different distances from the injection site, and you can see how there's less CO2 coming up, so it's more getting mineralized. And then you can tell how the percentage of mineralization. Because all the CO2, otherwise it's gone into the minerals. Thanks.
Questions tonight?
Hi, great talk. Really appreciate it. I'm just curious for the injection wells, have you noticed over time the pressures increasing at all? And kind of what does that tell you about the reservoir conductivity or clogging over time? And then the second part to that question is, have you done any tests with increasing the pressure, like step rate tests, to understand if pushing some of these fluids out further into the reservoir will help with not clogging the near wellbore with mineralization?
So thanks. We analyzed the pressure and the temperature in the well at the same time as we're injecting, but we don't want anything to be changing, and it's not because of course you're injecting fluid into the reservoir, but there's changes. But it's a bit different in this case because we're working in the geothermal reinjection area of the geothermal power plant, where it has like the reinjection site, and then elsewhere they're doing geothermal, so they actually what's the opposite of injecting? They're producing and taking up brine and fluids and steam from there, so it actually stabilizes very well. The pressure that we're injecting into slightly depends on the concentration of the CO2. So for example, this site, the first one, it's 6 bar, but then wherever we go, if it's less concentration, the pressure will increase because you need to keep the CO2 dissolved when you're injecting it, and then of course you have the hydrostatic pressure underground. So we haven't tried, because we want to just have it stable, we haven't done tests on that. But that would be something you could theoretically try and research as a limitation.
Okay. Yeah, I was just thinking about the lifetime of the well, and kind of going back to that paper you referenced about how there's a lot of pore space available over like a 10-year period. It only filled a small amount. Was that a theoretical or a modeling-based approach? Okay,
yeah.
Great. Thank you.
And maybe I'll just add a side note with the pressure. So you could also theoretically inject supercritical CO2, and there's other research groups around the world that are looking at that, because then per minute you can inject more CO2 because it's more concentrated. So you just inject a lot of CO2 at the same time, which is a benefit to that, but then there are other limitations. Then the CO2 is not, then it's buoyant and it can start going back out, so it's not trapped. Then you need a cap rock. They're like different, which are great, and those projects should also continue, but it's just a different way of doing it. And then you had the pressure, and yeah, everything has a pro and a con. Thank you.
Any more questions? Yeah. So in Iceland, I imagine it being a pretty tectonically active area. How do you deal with sort of earthquakes and other seismic hazards that might make unintended porosity where you're pumping things into the ground there?
Well, for this, it would still, because let's say worst case scenario, we have a big earthquake that goes through 50 meters from the injection well where, you know, the fluids are flowing, but there's still fluid, so they wouldn't start going up. So they would still be in the subsurface. Yeah, of course there might be some problems maybe on the surface, that things would move around. But then again, so we do get up to 7 magnitude earthquakes in Iceland, which can be quite big, but they're mostly in the south of Iceland. The others in Iceland, even though it is very seismically active and we get really many earthquakes every year, it's quite small, so they're not, yeah. And also, usually the epicenters of earthquakes are a lot deeper because we're injecting just 500 to 2,000 meter depth, and epicenters of earthquakes, it's not touching like the epicenter area, but it's definitely something that's good to think about when we go to new areas. Yeah, but I would visualize it behaves like groundwater, right? So it would just flow with the ground, maybe move direction, maybe go somewhere else, and then we just deal with that when that happens. Maybe we have to do new monitoring wells in that area.
Cool.
Thank you.
Thanks. I do have a question too.
Yeah.
Yeah, you were mentioning that you can keep injecting over 10 years on the same site, or at least you cite a study that
We
say
can
that.
probably do a lot more, but that was just as an example.
And I was wondering if you are checking the rate of mineral carbonation over, over time. I mean, how does that evolve?
It would probably one day start decreasing, but at least in the next decades, because let's say the main plume is going in this direction and it started dissolving and all the carbonates fill up here, maybe more of the pore space or something. Groundwater will just find another way or go farther away. But yes, like one day we'll maybe stop injecting into that one well and make another well nearby. But we're talking a bit, at least in the decades, at least from modeling, as far as we know. We'll have to, of course, be monitoring it. But I would say, if I put my science thought hat on, I would say it would probably just go further in different directions away.
Any other questions? Well,
thank you so much.
I have one last, actually. Sorry. It seems like all the operations are on land right now, and you were talking about potential offshore operation. When, if that happens, when is it going to happen in the near future, or we need to wait like a few decades?
It's definitely interesting because we always aim for low-hanging fruits first, because we want action and we want to get going and show that it works in a little step before we go to the big step. So now we're in the little step of using seawater. We've definitely talked about that we will go offshore in the future. But there's definitely a lot of complications when we start going offshore. We need to have a rig. We need to have both the CO2 concentration and electricity there. Maybe the public acceptance would be higher because it's not in somebody's backyard. But that's, it really simplifies having it onshore, or then even would be near onshore. Maybe we can do 200 meters offshore, but not you could do it, but then also you need you would need a well that would go through the ocean and then into the rock underneath the ocean, which is quite a lot. You don't know the effects. Of course, there's always, if there's some risks, let's say, associated, maybe it's easier to deal with on land, like we can maybe clean it up easier, worst case scenario, rather than when we're out in the ocean, we don't really understand the ocean floor that well. I have a lot of thoughts regarding this. It's really exciting, but I feel like we need to do the first step first, and then we will see where it goes, I think.
Great. Thank you very much, Katrin, and we will give you another round of applause.